So let's start with U star. So the question is, how big is U star, right? So to get an estimate of this, let's go through just a few steps of analysis, and maybe it'll help us as we're going through this to sketch out a few things. So we say over here, this is our velocity. On the y-axis, on the x-axis, we have time. And if we plotted the velocity at some position, right, like this, you're going to have an average that's occurring in that flow, and then there's fluctuations around that. So let's see. We'll denote the average here is U bar, and then the size of the fluctuation is actually, I need to maybe use red here. So the size of the fluctuation, as we define it, is going to be like half of the total oscillation, right? It's from the average point up to the peak velocity change. So this distance here, this is going to be U star. All right. So to get an estimate of this, I think it helps to think about what's going to be kind of limiting the size of the eddies as a function of position in the boundary layer. So to start, we're going to, let's see, estimate the shear stress in the flow. So we're going to call this estimate of shear stress our apparent stress, tau apparent. And that's going to be, well, it has to include both the viscous stress due to molecular diffusion, and it has to include the turbulent part of it. So our apparent shear stress is going to be this here, which is just mu du bar dy minus rho over t int times the integral of 0 to t int of u prime v prime dt, right? Just this thing here, basically, that's our apparent shear stress. So as we get really close to the wall, but maybe still outside the viscous sublayer, we're outside the region where flows laminar, there is turbulent flow, but we're still really close to the wall, because remember the viscous sublayer is tiny. What's true? Well, it's true that we're outside the viscous sublayer, so this part becomes unimportant, the first part, the molecular part. And so then we can say that actually this tau apparent is approximately the same thing as the shear stress at the surface, tau s. Okay, so that's one observation. And then over here, we can say that this whole integral is going to be approximately order of magnitude equal to rho times u prime, or sorry, so what's the magnitude of u prime? We decided it's called U star and V prime. So if U prime and V prime are about the same, this ends up being U star squared. All right, so we make just the couple observations there. So then we can say, all right, our apparent shear stress here is tau s. That's the shear stress at the wall. That's going to be approximately equal to rho times U star squared. A hard time making stars on this thing. Okay, so it's approximately equal to that, which is gives us the following. So it tells us that U star is, let's say, equal to the square root of tau s over rho, just solving for U star. Right, this gives us a rough estimate of the size of U star. So now we just need to figure out what's my shear stress at the wall. And then we have a good estimate of U star for this flow. Okay, let's see. So let's write this out instead in terms of our inner velocity. Right, so if we just say this in terms of inner velocity, it would be U plus is equal to U bar over U star, which is then using this thing we just derived, it's just U bar times the square root of rho over tau s. Okay. So this is our estimate for the size of u star, and then the inner velocity is a function of the size of that. Again, we don't yet know the shear stress, but we can get to that. Okay. So that's how big is u star. The next question is how big is which one here? So how big is the viscous sublayer? That L characteristic VS, how big is that thing? So let's see, let's go through kind of the same thing here. We're going to look at our equation. We're going to say very close to the wall, we have our apparent shear stress is equal to mu times du bar dy minus rho over t int, integral 0 to t int, u prime v prime, so v prime dt. Now, okay, if we're concerned now with the viscous sublayer and not with the turbulent eddy size, we are actually moving into the viscous sublayer for this analysis and not in the turbulent region. So in the viscous sublayer, there are no eddies, right? So this term goes away, the second term there. And we're left with our apparent shear stress at the surface is going to be equal to just our molecular contribution. So we write that as tau apparent is approximately equal to mu du bar dy, which is actually the same thing as our shear stress at the wall because we're so close to the wall. Right? There's not been much opportunity for loss as we move away. Okay. So just rewriting this now slightly, we'll say solving this for du. So this is going to be du bar. Sorry, clean this up. It says du bar is approximately equal to tau s over mu times dy. And then let's integrate this from 0 to u bar. Okay, and then that's going to correspond to an integral over here from 0 to y. And then we get u bar is approximately equal to tau s over mu times our position y. Okay, so let's see. This is kind of helpful, but kind of doesn't quite get us the full way. So what we need to do is we need to think about the fact that as we move away from the wall, the size of the fluctuations is kind of limited by just space, like just how much space is available for these fluctuations to happen. So if we sketch this out, let me just draw a little image here. So if we sketch this out, and this is y, and this is u bar, so it's our velocity as a function of position y. What we'd see is that, let's see, so we'd see that there's kind of this linear relationship here, like this. So there's kind of a linear relationship between these two things very close to the wall. So as you know, right, you're right near the wall, the velocity is going to be 0, so you really can't have any magnitude to any oscillation. So there's going to be this kind of critical point here, or a cutoff, where we'll say that at some point you're far enough away from the wall, you're far enough away that there's an opportunity for these eddies to occur. And so that ends up being our u star, right? The size of the velocity is going to be approximately equal to, or it's going to be equal to tau s over rho, right? That's what we decided before. So if you look at that and then look at where is this going to occur, it's going to be at this critical length, L characteristic Vs, and look at then the slope of that line. Right, we're trying to figure out how far we have to go out. The slope of that line is going to be u bar. So u bar is going to be tau s over mu times y. So this is all telling us that u star is approximately equal to tau s over mu times L characteristic. All right. So that's a bit confusing and kind of tortured way of getting to this conclusion that says our velocity magnitude is going to be proportional to the shear stress at the wall divided by the molecular viscosity times the characteristic length of the sublayer. Right, so this is now relating the magnitude of the oscillations to the boundary layer viscous sublayer thickness. Okay. So let's see, we can take one more step here and solve this. We could say L characteristic is equal to then just U star times mu over tau S. And then in terms of inner coordinates, which I'll write over here, inner coordinates, this is going to be y plus is equal to y over L characteristic Vs, which is then, we substitute in our L characteristic there, and we just get y times, let's see, tau S over U star times mu.